Hi guys, welcome back to my channel. Let's talk about sound today. So sound, just like light, it's a kind of wave, right? And then I break this video into 4 parts. So we're first gonna dive into the basics of sound, and then we're gonna do the famous decibel equation to do some logarithm. Then we're gonna move on to Doppler's effect, and finally the harmonics, okay? So let's dive into the basics. So the first thing you need to know is the speed of sound in air at sea level, which is 343 meters per second. Sometimes this is not provided on MCAT, but you want to know this. You want to have this in the back of your head, just like the speed of light in vacuum, which is 3 times 10 to the 8th meter per second, right? You want to know this. Okay, so traveling in air is just one medium that the sound can go through, right? The sound can also travel through solid, let's say the wall in between your bedroom and living room, right? Or liquid, or other gas besides air, right? So if I were to rank the speed of sound traveling in these different mediums, I would say the sound travels fastest in solid, then liquid, and then slowest in gas, okay? So this is the case for sound, but it's opposite for light. So for speed of light, actually, it travels fastest in gas, okay? So that's light, and then vacuum, okay? Okay, perfect. So that's different. Okay, and then to quantify the speed of sound, we have this equation that C minus the square root of B over rho, okay? And then C is just the speed of sound, just like the speed of light. We use C to denote it, right? And then this B is a bulk modulus. And then this is the density of the medium on the denominator. Whether it's a solid, it's some liquid, or some gas, okay? Different density of a different medium. Okay, so MCAT really asks you to really compute a specific speed of sound in a certain medium, right? It really tests you more conceptually, okay? So for example, a question can ask you, which one of the following choices explains that the speed of sound in water is larger than the speed of sound, let's say V water is larger than the speed of sound when it travels in air, right? And then I can say, okay, answer choice A is, because the density of the water is larger than the density of the air, right? So you don't want to be tricked. You don't want to choose that, even if it's a fact that the density of the water is larger than the density of the air. But this is not my correct answer choice, right? Why? Let's break it down, right? So if I were to compare the speed of sound in these two different mediums, I have this square root of B water over rho water, right? Versus the square root of B air over rho air, okay? So if the density of the water is larger than the density of the air, but the density of water is the denominator. So this term being larger will make the whole thing being smaller, right? And then that doesn't align with the fact that the sound travels faster in water, okay? So the real reason why that I can explain why the speed of sound in water is faster than the speed of sound in air is really because this B water is way, way, way larger than the B air, so that it compensates the differences of their densities, right? And then this bulk module is really inversely related to the compression. How compressible, okay? How compressible something is, okay? And then because water is less compressible than air, right? It's liquid. Air is, it's just everywhere, gas, so it's more compressible. So that because of this, we say that the B of water is really larger than the B of air, right? Okay, I actually have wrote it out here already. Okay, yeah, it's just inversely related. So the other way to phrase my choices, I can say, okay, answer B is saying, okay, water is less compressible than air. Or I say air is more compressible than water. Then this will be my answer choice. Okay, that will be the correct answer. Okay, so that's about the equation. And then also, if you have noticed from the equation, since the denominator has to have some density, right? to give the sound some speed, then we know that the sound really doesn't travel in vacuum, right? Not like light, right? The equation doesn't involve the density, at least not in the denominator of term, right? So that light can travel in the vacuum. And then this 3 times 10 to the 8th is really, it's a speed in vacuum, right? But we can round it to the speed of light in air as well. But the sound really doesn't travel in vacuum at all, okay? Since there's no density of a vacuum, all right? Okay, so that's the basics you want to know, okay? Okay, now let's move on to the decibel equation, okay? So the decibel equation is this dB equals 10 log I over I naught, right? So you've seen this equation a lot of times, right? And then what this really describes, this dB is really the loudness of the sound, right? And then this is the what? Intensity of the sound. And then this is really the base intensity of sound. What does that mean? That means it has to have that minimum. It's a constant. It has to 10 to the negative watts per meter squared. That's the minimum intensity the sound needs to make you hear it. The minimum intensity, that makes human be able to hear this sound. So that we know, okay, from this equation, we know that, okay, the intensity of the sound and then the base intensity, they both decides the loudness, right? The perception. You perceive how loud the sound is, okay? So that's a relationship here, okay? So MCAT is also like, you don't see those very often, those plug-in questions, right? They provide you 2 variables and then ask you to compute the 3rd variable. That's pretty rare, right? They do it with Doppler's effect, but not in this case. So in this case, they would test you in a more nuanced way, a tricky way, testing how you can manipulate the logarithm. Okay, for example, the problem can say, okay, so there's a speaker, right? So it's playing some music, and then the loudness goes from 10 decibel to 30 decibel. Okay, it gets louder. Okay, you turn up the volume, it gets louder. So I will ask you, okay, so this change of the decibel, the loudness, how does that change the intensity? Sorry, I just blanked for. So how does that change the intensity of the sound, right? So how you do this is that, okay, so the change, the delta decibel is really 30 minus 10 equals 20 decibel, right? So that's the difference. That's the difference of the decibel. So we can really use the difference of the decibel to calculate the difference of the intensity, okay? So it's 20 decibel equals 10 log I over I naught, right? Okay, and then that will give me log I over I naught equals what? Equals 2, okay? So that equals to log 10 to the 2 equals 2, right? You know that, right? So which means what? Which means I over I naught equals 10 to the 2 equals 100. And then this I naught is constant the whole time, right? So it's this I here, this thing is the change of the intensity, which is a factor of 100, right? So the answer is really intensity increased by a factor of 100, right? So this is the answer, okay? So let's do a couple more examples. So what if I say the decibel changes from 10 to 40, right? So the difference is really what? It's really 30. It's a really 30 decibel. So that will give me what? 10 to the 3, right? So that will be 1,000, right? Okay, what if it goes from 10 to 50 decibel? Then the difference is 40 decibel, and then that gives me 10 to the 4th. So it will be really 10,000, right? The intensity increased by a factor of 10,000. Okay, so that's how you quickly do it. And then if it gets trickier, if it gives you this condition, this in a question stem, it's okay, this is how the decibel changes, how the loudness changes, but it doesn't ask you to answer how does that affect the intensity. Sometimes it would ask you to, how does the pressure, the sound pressure change, right? So in this case, you still need to compute this a factor of 100 first, and then you get the intensity changes increased by a factor of 100, and then you know the relationship that I squared is proportional, is directly related to pressure. Then if you know, okay, I increased by a factor of 100, then you will know, okay, then P increased by a factor of 10,000. Right? That's how you do it. You square this, right? Okay, so that's pressure. Okay, what about amplitude, right? It gives you this again. How does the decibel change? How does the loudness of the sound change? And then how does that affect amplitude of the sound wave, right? And then you have to know the relationship that the intensity is proportional to related to the amplitude squared, okay? So once again, if my intensity increased by a factor of 100, then my amplitude increased by a factor of what? 10, okay? So that's the actual relationships you need to know regarding intensity, pressure, and amplitude, okay? All right, I hope that's helpful. And then now we can move on to Doppler's effect. Okay, Doppler effect. So Doppler effect, you may have heard about this famous equation that it calculates the frequency, right? So say the new frequency or frequency that is perceived, right, equals the original frequency times this speed of sound in any medium, and then plus minus VO, and then this is this, right? Vs. Okay, so this is an super annoying equation, right? Because you can never just really get it right? When do you use plus? When do you use minus? In physics class, we learned that, okay, when it's going away, whatever, plus or minus. I never memorized those. I don't know. I just can't do it, okay? So I came up with a common sense way for you to instantly know if you need to use plus or minus or minus or plus, okay? So let's first go over some common sense, okay? And then the common sense is really, that as you are approaching something, right? Let's say this is a car, right? And then there's a siren that on top of the car, it's a police car, let's say, goes off, right? And then you are here, okay? So this is you. You're the observer, right? This VO is V observer, the speed of your movement, your displacement, right? And then the source of the sound, the source Vs, right? Vs describe how fast does the source travel, the speed, the velocity of the source in this case is the police car, right? That's what VOVS describes, right? And then this V is really if the sound is traveling in air, because in this scenario, right, it's all happening in air. So then this is really 343 meters per second, right? The speed of sound in certain medium, okay? And then this V naught is the original frequency of the sound, right? Emitted by this siren of the police car. So this will also be provided, right? Okay, so these are the variables in this equation, okay? And then let's talk about common sense, okay? So if you are approaching this person or this observer is approaching the car, no matter what the case is, either one, they are getting closer by each other, right? They're getting closer and closer. So that using your common sense in your real life, if you walks towards a police car, a fire truck, whatever, do you feel like the pitch of the sound goes up or down, right? The pitch goes up. It gets really sharp, right? It was dull when you were far away from the sound, right? So that we know the pitch, the frequency. I'm not saying that pitch equals frequency, but on MCAT, it's easy for you to conceptualize it, right? So the pitch goes up, the frequency goes up, okay? All right, and then the other opposite case is when the car is really traveling away, the siren, right? It is really traveling away from this observer, this person. Then you can imagine the frequency of the sound goes down, right? That's not hard. That's intuitive. That's common sense. That's your life experience, right? So that you know that, okay, the result of the result is I perceive a higher frequency, okay? So if you perceive a higher frequency, then this frequency perceived would go up, right? It would go up. And then these numbers are provided for you in a question stem. So you just need to know if you need to plug in this plus VO or minus VO. In this case, if I want this to get larger, then this thing on my denominator, it has to what? Go up. You don't want to subtract VO from V. You do want to add something to make this part large, right? And then the denominator on the opposite side, you want to subtract VS from V to make the denominator smaller. So the whole thing can be larger, right? So that's the case when we get closer to the sound, the frequency, the perceived frequency, not the real frequency. The real frequency, the original frequency is that the VO that will be provided to you, okay? So perfect. So really, you just need to plug in. You plug in all these 4 numbers, right? VO and then V and then VO, VS. You just plug it in. You don't need to think about it. And then you just decide, okay, so I'm getting, they're getting closer by. According to my common sense, the frequency goes up so that I need to add VO on top of V and subtract VS, right, from V in the denominator, okay? So that's about this. And then what about the other case? The other case, the frequency is going down, right? So if you want the thing to going down, you really want this VO to be subtracted from V, right? You want to use a subtraction. And then in the denominator, you want to increase the denominator so the whole thing can be, once again, decreased, right? So you want to plus the VS to increase the denominator, okay? So I hope that makes sense, right? That's really common sense, that you never need to memorize if it's plus or minus. You just need to sort out the scenario in a question stem, whether they're getting closer by or getting farther apart, okay? That's it. Okay, so now let's do a tricky problem, okay? So the tricky problem now, let's apply it to our biological application. Let's say I have a blood transducer, okay? Okay, so blood transducer is just some type of sensor that they put it on your skin, right? And then it tests a bunch of things, the pressure, let's say it also tests the frequency of the blood, okay? There's a sound, right? The blood movement creates a sound. Okay, so in this case, this scenario, and then I'll provide you, okay, the sound that travels in your blood has this a frequency of 20 hertz, okay? And then the velocity when sound travels in your blood, which is liquid, so it's not going to be 343 meters per second anymore. It has to be what? Smaller, right? Remember here? Remember here, the liquid, right? It travels slower in liquid. So let's say 243 meters per second when a sound travels in blood, okay? In this liquid. Okay, and then I'm gonna ask you, oh, there's one more thing I need to give you. I would say, okay, the speed of your blood, your moving blood travels at 2 meters per second. Is that too much? 1 meter per second. I mean, let's do 0.5 meters per second, okay? So that's more legit. Okay, that's how fast your blood travels. How fast the sound travels in your blood. Okay, all right. So I'm gonna ask you, please calculate the perceived monitored, the sensed frequency of that sound, according what would the transducer show? Okay. Do you understand my question? And then you're like, oh my gosh, that's a challenging question. There are a couple of things you need to sort out, right? So you know that it's asking you to use the equation, this F equals F0, and then VO, and then V minus plus VS, right? Okay, you know this is the equation that you need to use, but you're like, okay, which number do I plug in where, right? So you have to think about it. So the transducer, the machine, is sensing the perceived frequency, right? So in this case, the observer, the person that we have in this case is the transducer, right? Okay, and then what about the source? The source is really the moving blood, right? Source is the moving blood. Okay, so that we know. Okay, very good. Now we know this VS is 0.5 meter per second. And then this VO, I'm not sure yet, all right? And then this V is 243 meter per second. This V is also 243 meter per second. meter per second. And then this FO, we know is a 20 hertz, right? Okay, we plugged in everything, and then we want to calculate the perceived F, the frequency, but we don't know this, right? We don't know VO, but you need to think, right? It might be hard for you to think on MCAT. You only have about a minute to solve every single problem, but let's think here so that we don't spend time thinking on MCAT. We don't freeze. We don't get anxious, right? So the VO, in this case, this VO is me, right? So this VO can travel, 1 meter per second or whatever. This thing can travel because it's a person, right? But in this case, the observer is really the monitor, the transducer. It's a machine, right? Does it travel? No, they just put it on your skin. So this VO is really what? 0 meter per second, right? Is that legit? Of course. Yeah, of course the VO can be 0 meter per second, right? And then also we know that to sense the sound, the new frequency, your blood must be traveling towards this transducer so that the transducer can sense, can observe, right? Can observe the new frequency. So in this case, we will use this plus and then this minus case, right? So because the goal is to make what? Is to really make this go up, right? As they get close by. Okay? All right. I mean, I should use blue because I used the blue in the case of increased perceived frequency. Okay, so let's just align that. Okay, perfect. So that's it. Okay, that's as tricky as it gets, right? Application to the biological scenario. Okay, so I think we are ready to move on to the harmonics. Okay, so what about harmonics? So harmonics is basically music, right? So music, we can have a string that two ends are both closed, right? But in this case, I drew the picture, it's a pipe, right? But the equation that you are gonna learn is apply both to both the closed end string, closed end. This is closed end, and then closed end, right? So the pipe and string, okay, the equation I'm about to talk here, this equation apply to both the case of string and the case of pipe, as long as they're both closed on their two ends, okay? All right, and then they also apply to open string and pipe, okay? Okay, I'll give you a couple musical instrument examples in just a second. Let's just first go over the equations, okay? So in this case, I have a question for you, which is, do you think this is the full wavelength or this is the full wavelength, right? So the answer is this whole thing is one full whole wavelength, lambda, okay? So on MCAT, they would always ask you to either calculate, give you the length of the pipe, okay? So for example, I say this length is 2 meter, okay? Is 2 meter. And then this case of a first fundamental frequency. Okay, and then this is the second harmonic. This is the third harmonic. Okay, all right. So the first fundamental frequency, if I know the pipe is 2 meter, and the equation is really, I mean, before we dive into equation, if I tell you, this part, this length is 2 meter, this pipe, how long is the wavelength, right? And then you would know the wavelength is what? Is 4 meter, right? Because it looks like twice the length of the pipe, right? That's true, right? But you need an equation to solve scenarios like the second and third harmonics, right? When the picture gets crazy, right? Okay, or if they don't ever provide you a picture on MCAT, right? So the equation you use is lambda, wavelength equals 2, right? Double, twice, right? 2 times L over N. N equals 1, 2, 3, 4, 5. So if the first fundamental frequency, it is you plug in 1. And then in the case of a second harmonic, the N equals 2, right? And then this N equals 3 for the third harmonic, okay? So let's calculate it. So the wavelength, if we don't look at a picture, use the common sense, we say, okay, lambda equals 2 times what? How long is the pipe? 2 meter, okay? And then what is N? N is 1. And then that gives you what? 4 meter, okay? And then if we were to calculate this second harmonic, it's also called the first overtone. So this will be second overtone. over tone. Okay, so that the lambda equals what? Equals 2 again, and then it's a 2 meter, but the n is what? N is 2 now, right? It's the second harmonic. So that gives me what? That gives me 2 meter, right? So you can see the second harmonic, really, the wavelength equals the length of the pipe, right? Okay. It also applies to string, okay, just so you know, just to emphasize that again, because a lot of musical instruments, they're close string, okay, not pipe. Okay, perfect. So if the question gets trickier, it doesn't like explicitly tell you, oh, the length of the pipe. It tells you the wavelength of the second harmonic. Then you will know, oh, the length of the pipe is 2 meters, right? And then you can use that length of the pipe to calculate the wavelength for the third, fourth, and the first harmonics. Okay, so let's do another one. Let's say the problem tells us, okay, the problem tells us the wavelength of the second harmonic is 2 meter. Okay, then please solve the wavelength of the third harmonic. Then I immediately know that, okay, so this wavelength of the second harmonic equals to the length of the pipe, right? So my wavelength of the third harmonic would equal to 2, all right? Again, the equation, and then the length is what? 2 meter, and then over 3, right? So that gives me 4 over 3 meter, which is the wavelength for my third harmonic, okay? So I hope that makes sense, okay? And then you can also be given wavelength to calculate the length of the pipe, right? So you just rearrange it, okay? So this is n, okay? All right, so once again, the n is 1, 2, 3, 4, 5, easy, okay? And then this applies to, let's give you a couple examples, right? For example, guitar, this is a close string, right? Or what else? Piano is also applies to this scenario, okay? Or we can have a cello, right? We can have cello. And then we also have this case, this is a trumpet, that is the open case. Okay, open case, close case. They all use this equation here. Okay, perfect. So now let's move on to a different scenario. Okay, so this scenario is really not open or close. It is really closed open. Okay, and then the difference you see, I'm going to use a different color. The difference you see that whenever you have closed material, right, you have this node here, right? This is a node, and then this is anti-node, okay? And then if I open this up, now this is not closed anymore. This is open, okay? So we go to here, we go to open. Then once it's open, you cannot have any node on this open side. All right, you can only have anti-node. Okay, and then this side is closed, so it's still a node. Okay, you can only have anti-node. That's why you can imagine. So this thing is really pretty and symmetric, right? The case of this close scenario, right? It's really symmetric, because if I were to break down my wavelength to four, part 1, part 2, part 3, part 4, you can see, oh, it's really pretty here. But here I can't make it pretty anymore. I have to scooch over. I have to scooch to the right side, right? Because this open part can only have an anti-node, okay? So that makes, if I were to complete my wavelength, then you will see that this is my whole wavelength, right? So really, in a pipe, if I were to divide it to part 1, part 2, part 3, part 4, then you see it's really 1/4 of the wavelength that is inside this pipe, right? So this is the reason why the equation, the wavelength, is really 4 times the L over N, okay? So let's say, for example, the L is again 2 meters, right? Then for this first fundamental frequency, your wavelength is really 4 times the 2 meter of the length of the pipe over 1, right? That will give me what? Give me 8 meter, right? It looks intuitively correct, right? Because as I have a 2 meter here, and that's just 1/4, and then 2 meter, 2 meter, 2 meter, 2 meter, that's 8 meters, right? So that's really intuitive. You can visually see it on the picture, okay? And then now let's explain why when we move on to the second and then the third harmonic, the n doesn't equal to 2, n doesn't equal to 3. Instead, n equals to what? to 3 here, and n equals to 5 in this case. It's the 13579 this case, okay? It's the same reason, because as you can see, I have open end here, so I can't really, for my second harmonic, I can't have something pretty like that. Something pretty and symmetric like that. Right? Like the case here, the second harmonic of my closed, I can't. I have to scooch over to the right, right? All because I have this open end here, so that I can only have an anti-node here, right? So I can only have an anti-node here, so I kind of scooch over to the right, and then I can expand it. I elongated my wavelength, if you will, right? So I have to do this due to the structure of the pipe, right? Okay, so in this case, if I were to complete this, right? So you see that if I break it down into 1, 2, 3, 4, 5, 6, 7, 8, right? So that gives me two wavelengths. And then you see that really it's the 1, 2, 3. 3 over 4, they are inside a pipe. Okay, so that's why when we divide it, it's lambda equals 4 times 2 meter over 3. Okay, and then in this case it will be 1, 2, 3, 4, 5. Okay, so I'll have lambda times 4 times 2 meter over 5. Okay, so I hope you can visually see it. Okay, why it's always the 1, 3, 5 instead of a 1, 2, 3, 4. Okay, so let's give you some example. So what kind of a musical instrument apply to this? Okay, I would say we have a flute. Okay, flute is when you apply to this. Okay, and then by the way, there's one more case that you use the equations for this closed scenario. Is if they say, okay, I have a string, and then that string is attached to the wall. Okay, so I have a string, but it's attached to the wall. Then you know it's also closed string, right? Closed pipe. You can think like that. Okay, so you would use this. Okay, just in case they play this wording game. Okay, all right. So that wraps up harmonic. Okay, so the very last thing I want to point out is we know that wave, we can have longitudinal or transverse wave, right? And then in the case of a pipe, it's different than the case of string, right? The pipe is a longitudinal waves, where the string is really the transverse wave, okay? And then all the other electromagnetic waves, like the radio waves, the UV light or the visible lights, all these things that you memorize, you also have to memorize the ranked order, right? Which one have the largest wavelength, and then which one has the small. And so all the electromagnetic waves are also transverse waves, okay? All right, so that's all I have for you about sound. I elaborated this a little bit, but I hope that's all helpful.